The history of electromagnetic theory begins with ancient measures to understand atmospheric electricity, in particular lightning. During that time, people had little understanding of electricity and were unable to explain the phenomena. At the dawn of 18th and 19th century, philosophical and religious ideas led many scientists to accept the argument that seemingly separate forces, for example electricity, magnetism, light, shared a common and fundamental source. In addition to a search for a common source of all natural phenomena, an elusive ether through which light could pass was thought necessary to explain the wave-like behavior of light. In the 19th century, it had become clear that electricity and magnetism were related and their theories were unified. Wherever charges are in motion, electric current results, and magnetism is due to electric current. The source for electric field is electric charge, whereas that for magnetic field is electric current, charges in motion. Scientific understanding into the nature of electricity grew throughout the 18th and 19th centuries through the work of researchers such as Coulomb, Ampere, Faraday, and Maxwell. Born in France and baptized at the parish church of Saint André, Charles Augustin de Coulomb studied philosophy, language, and literature. When his father suffered a financial setback, he was forced to leave Paris and went to Montpellier, where he submitted his first publication to the Society of Sciences in Montpellier. He graduated in 1761 and joined the French army as an engineer in the rank of a lieutenant. Over the next 20 years, he was posted to a variety of locations where he was involved in engineering, structural fortifications, soil mechanics, as well as other fields of engineering. Coulomb's law, which you can see at the right hand side corner of the screen, or Coulomb's inverse square law, is an experimental law of physics that quantifies the amount of force between two stationary electrically charged particles. The electric force between charged bodies at rest is conventionally called electrostatic force or Coulomb force. Although the law was known earlier, it was first published in 1785 by him. Hence, the name Coulomb's law was essentially to the development of the theory of electromagnetism, and maybe even it is considered as a starting point, as it made to possibly to discuss the quantity of electric charge in a meaningful way. André-Marie Ampere was born into a well-to-do family in the city of Lyon, France on January 20, 1775. His father was Jean-Jacques Ampere, a businessman. The education of André-Marie received was rather unusual. His father was a great admirer of Jean-Jacques Rousseau, one of the leaders of the French Enlightenment. He decided to follow Rousseau's approach for André-Marie's education. This meant no formal lessons, although as a child of the French Enlightenment, André-Marie did not reject the church and remained a practicing Catholic throughout his life. At the age of 13, André-Marie began a serious study of mathematics using books in his father's library. He submitted a paper about conic sections to the Academy of Lyon, but was rejected. Ampere began by repeating Orsted's work, and before the end of September 1820 he made his own discovery. He found that if electric current flows in the same direction in two nearby parallel wires, the wires attract one another. If electric current flows in opposite direction, the wires repel to one another. Ampere had discovered something amazing. He had produced magnetic attraction and repulsion in the complete absence of any magnets. All of the magnetism was generated electrically. He called this new phenomena field of electrodynamics. Ampere then brilliantly found an equation which is right there on your screen, an equation connecting the size of magnetic field to the electric current that produces it. The story of Michael Faraday's life is one of the most romantic stories in the annals of science. It will continue to inspire in countless ways. Faraday rose from a bookbinder's apprentice to become one of the greatest scientists of all time. He is acknowledged as one of the greatest thinkers of his time. He was a true pioneer of scientific discoveries. His discoveries have had a spectacular effect on successive scientific and technological developments. Faraday attended a day school and received only the basic education to read, write and count, that is the traditional 3 R's, reading, writing and arithmetic. Given his family background, nothing much could be expected. The Faradays were desperately poor. When Faraday was 13 years old, he had to find work to help the family finances. Faraday learned the trade of bookbinding, as well as is evident that in later years he bound many volumes for himself, and many of them are still in existence. He was a great builder of instruments. Faraday was a great popularizer of science. He initiated popular science lectures for children and general audiences at the Royal Institution. Faraday's law of induction is a basic law of electromagnetism, predicting how a magnetic field will interact with an electric circuit to produce an electromotive force, abbreviated as EMF, a phenomena known as electromagnetic induction. It is the fundamental operating principle of transformers, inductors and many types of electrical motors, generators and solenoids. The time that we are talking about was then when scientists understood very little about the concepts and ideas like electricity and magnetism. Truth to be told, they knew even less about the relationship between the two. But they were starting to study, explore, experiment, dig, so to speak, into the mystery of the universe. German physicist Heinrich Lenz made an enduring contribution, I would say, to physics. Lenz's law, and in doing so he made his mark on magnetic history. Lenz was born actually in Estonia. He studied chemistry and physics both at a local university and travelled with famous navigator who was on his third world expedition. It was during his expedition that Lenz began to study the physical properties of seawater or salt water and other climatic conditions. Post-voyage, he began to work in St. Petersburg, Russia, later serving as a dean of mathematics and physics and a senior official in academics. He also started studying, you guessed it right, yes, it is electromagnetism. Lenz's law, which is there on your screen at the right hand side bottom, says that the introduction of a conductor within an electromagnetic field will produce an electricity inducing an opposite field that repels the magnetic fields, producing the charge. It is basically a consequence and the conservation of energy. According to this law, the total energy in the universe must remain constant. If the field that is associated with the current moves in the same direction as the charge in the magnetic field that created, the two fields would combine and create a net field that would induce a current with double the magnitude. But there was a problem. The problem was that all these equations which you can see on your screen are concepts, I would say, which were scattered. The concepts of electricity at one hand and magnetism on the other hand were seemingly same concepts which looked to emerge at one place but was unable to find its way home. The wilderness of thought, the disparity of ideas seemed to kindle the idea of unification. The two concurrent forces of nature appeared to be generated from the same source, yet the source dispersed into the uncharted waters, which appeared as a mirage in front of physicists who were finding it difficult to grab the central idea. In 1819, 12 years before Maxwell was born, the field of electromagnetism was born. Hans Christian Orsted of Denmark had suspected that electricity and magnetism were related in some way for some time, and was finally able to create some evidence for it. So you see on the screen, he suspected electricity and magnetism were related. The first connection between electricity and magnetism was established. What he did was that he held a wire above the compass, and the compass needle was deflected by nearby electric current. So when a current traveled through the wire, he noticed that the needle of the compass moved. For this discovery, the Royal Society of London awarded Orsted the Copley Medal in 1820, and the French Academy granted him 3,000 francs. Orsted's findings stirred much research into electrodynamics throughout the scientific community, influencing French physicist André-Marie Ampere developments of a single mathematical formula to represent the magnetic forces between current-carrying conductors. Orsted's work also represented a major step forward, a unified concept of energy. The picture that you see on your screen is what is called a galvanometer, right? An electromechanical measuring instrument for electric current. A galvanometer works by deflecting a pointer in response to an electric current flowing through a coil in constant magnetic field. Based on Orsted's experiments that a magnet's compass needle deflects when near a wire which have electric current, Johann Schweiger at the University of Halle on 16 September 1820 designed what is called the world's first galvanometer. Schweiger was born in Erlanger, Bavaria, Germany on 8th April 1779. He was educated at the University of Erlanger, where he received his PhD degree in 1800. He used Orsted's discovery of electromagnetism for his invention. Schweiger developed the galvanometer as a tool for measuring the strength and direction of electric current. Schweiger, however, became one of the first scientists after Orsted's discovery to demonstrate a determination and an interest in experimentation of electromagnetism. As co-editor of the Journal for Chemistry and Physics, he probably read Orsted's manuscript submitted to the journal for review and publication. Schweiger then attempted through experimentation like Orsted the construction of large piles to improve the performance of electromagnetism. John Clerk, later Clerk Maxwell, a Midby, was a Scottish advocate and father of the famous physicist James Clerk Maxwell. He was born in Edinburgh on 10th November 1790, the son of Janet Irving and Captain James Clerk. He studied law and qualified as an advocate in 1811. He inherited the Middleby estate in the Dumfriesshire from his mother Dorothea Clerk. Maxwell, upon her death in 1793, assumed the additional surname of Maxwell. He was elected a Fellow of the Royal Society of Edinburgh in 1821, his proposer being Sir George Stuart Mackenzie. In the 1830s, he is recorded as living at 14 India Street in Edinburgh's second new town, which is where James Clerk Maxwell was born. He married Frances Hodgson Kay, daughter of Robert Hodgson Kay and Elizabeth Liddell. Their children included the mathematical physicist James Clerk Maxwell. James Clerk Maxwell was born on 13 June 1831 at 14 India Street at Edinburgh of Middleby. An advocate and Frances Kay's daughter of Robert Hodgson Kay and sister of John Kay. His father was a man of comfortable means. Recognizing the boy's potential, Maxwell's mother Frances took responsibility for his early education, which is in the Victorian era was largely the job of the woman of the house. At 8, he could recite long passages of Milton and the whole of the 119th palm. Maxwell was fascinated by geometry at an early age, rediscovering the regular polyhedra before he received any formal instruction. At the age of 18, Maxwell contributed 2 papers for the Transactions of the Royal Society of Edinburgh. One of these, on the equilibrium of elastic solids, laid the foundation for an important discovery later in his life, which was temporally double refraction produced in viscous liquids by shear stress. In October 1850, already an accomplished mathematician, Maxwell left Scotland for the University of Cambridge. In 1854, Maxwell graduated from Trinity with a degree in mathematics. He scored second highest in the final examination, coming behind Edward Routh, and earned himself the title of second wrangler. Maxwell's times at King's was probably the most productive of his career. He was awarded at Royal Society Rumford Medal in 1860. This period of life would see him display the world's first light-fast color photograph, further develop his ideas on the viscosity of gases, and propose a system of defining physical quantities now known as dimensional analysis. Maxwell would often attend lectures at the Royal Institution, where he became into regular contact with Michael Faraday. The relationship between the two men could not be described as being close because Faraday was 40 years Maxwell's senior and showed signs of senility. They nevertheless maintained a strong respect of each other's talents. Now here is something interesting which I would like to draw your attention. At the International Science Festival in Edinburgh in 1991, there was a unique meeting when there came together 2 members of the present generation who were related to James Clerk Maxwell and his lifelong friend and scientific colleague Peter Guthrie and Tate, professor of natural philosophy at the University of Edinburgh for over 40 years. Present were Sir John Clerk, 10th Baronet and great-grandson of Maxwell's uncle Sir George Clerk, and Mr. Tate, a great-grandson of Professor P.G. Tate. It was probably over 100 years since the Clerks and Tates had last met, a reminder of a unique era in Scottish intellectual life. Right on your screen you can see his father's side. All were great geniuses. James Clerk Maxwell came from a remarkable line of progenitors. You see here, he seemed to exemplify the relationship of his towering intellect to genetic inheritance. The famous concert pianist John Lell, after winning the International Tchaikovsky Piano Competition in Moscow, was asked where had he got his music from. So he was somehow perplexed by this question and unable to answer it, since none of the previous generations of his family had been at all musical. If James Clerk Maxwell had been asked a similar question, he would not have had to look very far for an answer. On his father's side, right here on the screen, he was a member of the Clerk family, the Clerks of Penicuik, and on mother's side, a member of the Clay family, the Kays of Northumberland. So you can see that his family lineage is very rich, and you can see from his father's side and his father's side, all were great people. The first paper that James Maxwell published after earning his graduate degree was a 75-page analysis of what is called Faraday's concept of lines of forces. Now, published in 1855 and was suitably titled On Faraday's Lines of Force, right? Now, Maxwell translated Faraday's ideas into mathematics. Maxwell created something which is right on your screen, which is called, vectors, right, to describe the main players of electromagnetism. So you can see here, E, the electric field of intensity, H, the magnetic field of intensity, B, the magnetic flux of intensity, and I, the electric current. E and H are forces and B and I are fluxes, which we will soon come to know. And a way to picture flux is there on the screen, is to imagine having a square loop of a wire or a flow of river. The flux of the velocity of the water would be considering how much water will flow through the loop. The flux of an electric field is proportional to the number of electric field lines that would go through that. On 16th of June 1865, James Clerk Maxwell's paper, electromagnetic, I would say, let us look into this paper once more. Yeah, so it says a dynamical theory of the electromagnetic field was sent to the printers Taylor and Francis for publication in Philosophical Transactions of the Royal Society. Now here is something quite amazing. Now 6 days earlier, on 10th of June of the same year, Richard Wagner's Tristan and Isolde had its world premiere in the Court Theatre of Munich. The word revolutionary is the only adjective which begins to do justice to the extraordinary impact of these two events of 1865, one in the physical sciences and other in music, opera and drama. Wagner's staggering innovations in musical harmony, structure and dramaturgy revolutionized the approaches of composers and profoundly influenced the music of the late 19th and 20th centuries. Music would never be the same again. On the right hand side, you see the gentleman. Maxwell's monumental paper laid the foundation for the innovations of the 20th century, physics, by placing fields at the heart of the theory of electromagnetism and all of the subsequent fields which describe how matter and radiation behave at a fundamental level. So this is quite an unusual analogy. Richard Wagner with his great opera Tristan and Isolde, and James Clerk Maxwell with his theory of electromagnetism. I just tried to show it because these two are both revolutionaries on each other aspect. So in 1865, when Wagner supported this on the 10th of June on the same year, so it revolutionized both music as well as what we call the theory of electromagnetism. Now what I would like to show you here is that these are the original Maxwell's 20 equations. So you see here, so this one is named as B on the right hand side. These are the 3 equations of magnetic force, 3 equations of electric currents, and 3 equations of electromotive force. Mind it that these are original Maxwell's equation, not the reduced one which we studied today. Going further, what we see is this. We find the 3 equations of electric elasticity, 3 equations of electric resistance, and 3 equations of total currents. And further, what we find is this 1 equation of electricity and 1 equation of continuity. Now if you add them all together, 1 plus 1, 2, and the earlier one, it comes to 10, right? So what I have done is that these are the reduced to 8 equations, which you can see earlier were the original 10 equations, and this thing obviously is taken from a website, so I feel happy to quote and bring before you the Royal Society Publishing right there in front of the screen. I've mentioned where from I have taken, along with the DOI number of the research paper and the Royal Society website, so that there is no confusion in the video. These are the 10 equations, original 10 equations, and these are the reduced 8 equations which we find. So this is kind of an historical context. So these are the reduced to 8 equations, right, as you can find it. Now, although Maxwell's most important equations has already appeared through his seminal paper entitled On Physical Lines of Force, which was written in around 1861, it was not until 1865. Now, this is the paper, as you see on the left hand side, this is the On Physical Science 1861. But it was not until 1865 that Maxwell created a distinct listing of 8 equations in his follow-up paper known as this one, A Dynamical Theory of the Electromagnetic Field. This was in a section headed as General Equations of the Electromagnetic Field. While Maxwell refers to 20 equations at the end of the section, however, there are in fact only 10 equations which I have just shown you. Maxwell arrives at the figure of 20 because he splits 6 of these equations into 3 Cartesian components. Now Maxwell's original 8 equations, if I see, are this. The first one, the displacement current. The total electric current is the sum of the conduction current and the displacement current. The second one, marked in red in a box, the flywheel equation, appeared as the 55th equation in part 2 of the original 1861 paper, which is on the left hand side, and it exposes the fine-grained rotational nature of the magnetic field. Maxwell identified Faraday's electrotonic state with a vector A, which he called the electromagnetic momentum. The vector A relates to the magnetic intensity H through the curl equation. Coming to the third, Maxwell's third equation is derived hydrodynamically, and it appears as Ampere's circuital law. Coming to the fourth, marked here in box of red colored, originally appeared as equation 77th in part 2 of his 1861 paper, and it takes this form. Coming to the fifth one, this is the elasticity, dielectric constant and permittivity. Maxwell's fifth equation is the equation of electric elasticity, which first appeared in the preamble of part 3 of his 1861 paper, and then again at an equation 105 in the same part. In 1864, the negative sign was removed and it appeared in this form. The sixth paper, which is this one, Maxwell's sixth equation is the Ohm's law. Coming to the seventh equation, which is this right at the bottom of your screen, this appeared as 115th in his 1861 paper, is the Gauss's law. And the last equation, which is right there at the bottom, is Maxwell's eighth equation, number 113 in his 1861 paper, which is called the equation of continuity. So this gives you a total idea of the original 1861 paper, the numbers, and the earlier the 10 I would say the 10 equations, and how it has been reduced to 8 equations. The self-taught mathematician, so this is the original equations. Again, I have taken from a researcher called Frederick David Thom. Here is I have taken it from ResearchGate. So here is the URL, and if you wish, you can go there. Now, the figure of the person standing on your left hand side of the screen is a self-taught mathematician and physicist Oliver Heaviside's parents were Rachel Elizabeth West and Thomas Heaviside. He was born on May 1815, Oliver the youngest of his parents' 4 sons, and he was born at 55 King Street in Camden Town. He caught scarlet fever when he was a young child, and this affected his hearing. This was to have a major impact on his life, making his childhood unhappy, with relations between himself and other child difficult. Now, in 1884, he recasted Maxwell's mathematical analysis from its original cumbersome form to the modern vector terminology. It reduced the equations down to 4 differential equations in 2 unknowns, as we know as Maxwell's equations. The 4 reformulated equations describe the charges, magnetic fields, and the relationship between 2. So the first equation right there on your screen relates electric flux to the volumetric change density. The second equation says, which is right on your screen, that a magnetic field does not diverge because there are no monopoles. The third equation summarizes the result from Faraday's electromagnetic induction. The voltage induced in a circuit was proportional to the time rate of change of magnetic flux through the circuit. And the fourth is from Ampere's law. The magnetic field in a closed loop around a current was in fact equal to the current through the loop. So these are the 4 reduced form which was done by Heaviside. Now, this is the Gauss's law of electricity, Gauss's law of magnetism, Faraday's law of induction, and Ampere's law, which has both differential and integral form. I'm so sorry. This is coming up in the next part of my video. Now, a treatise on electricity and magnetism, this is a 2-volume treatise on electromagnetism, which was written by James Clerk Maxwell in 1873. Maxwell was revising the treatise for a second edition when he died in 1871. The revision was completed by William Davidson Niven and was meant for a publication in 1881. A third edition was prepared by J.J. Thomson and published in 1892. The treatise is said to be notoriously hard to read, containing plenty of ideas which were lacking both in terms of clarity and orderliness, which was allowed to catch on more easily. So you see the transformed electromagnetism in 12 equations. A means the vector potential, B the magnetic induction, C the electric current, D the displacement, E the electric field, Maxwell's electromotive intensity, F is the mechanical force, H is the magnetic field, and this is the magnetic force. So this is later published by James Clerk Maxwell in 1873. Now, Maxwell's time at King's College London was probably the most productive in his career. He was awarded the Royal Society's Rumford Medal, which I have spoken earlier, in 1860 for his work on colour, and was later elected on the Society in 1861. This period of his life would see him display the world's first high-coloured photograph. Now he returned to Cambridge and became the first Cavendish Professor of Physics. Maxwell was put in charge with the development of the Cavendish Laboratory, supervised at every step in the process of the building and the purchase of the collection of apparatus. As a great lover of Scottish poetry, Maxwell memorized poems and wrote his own. The best known is Rigid Body Sings, closely based on Coming Through the Rye by Robert Burns, which he apparently used to sing while accompanying himself on a guitar. In April 1879, Maxwell began to have difficulty in swallowing, the first symptom of his fatal illness. Maxwell died in Cambridge of abdominal cancer on 5th of November 1879 at the age of 48. His mother had died at the same age of the same type of cancer. Maxwell is buried at Barton Kirk near Castle Douglas in Galloway, close to where he grew up. As death approached Maxwell, he told to a Cambridge colleague, "I have been thinking how very gently I have always been dealt with. I have never had a violent shove all my life. The only desire which I can have is, like David, to serve my own generation by the will of God, and then fall asleep." Well, that is all a brief idea on James Clerk Maxwell's life and the history of development of Maxwell's equations. In the next video, we would be talking about Maxwell's equations. We would deal with the detail on each and every aspect, component, and the mathematical part of Maxwell's equations. Do let me know your comment in the comment section. Don't forget to like, subscribe, and let me know how the introduction to Maxwell's equation with a formidable history, giving a clarity of idea from the development along with the historical part, and followed by Maxwell's equations, the researches, and the death of Maxwell. How did you like it? So stay safe, stay happy, and we all wish that this war gets over as early as possible. We have just ended with the pandemic, and we really don't want again a war to rage around the world. Stay safe, stay happy, and have a nice weekend ahead. Bye.